Besides using logarithms to measure earthquakes, we also use logarithms to make the scale that measures the loudness of sound more manageable. The human ear can hear sounds over a huge range of relative intensities, from rustling leaves to howling jet engines. Furthermore, the brain perceives larger changes in sound intensity as smaller changes in loudness. For example, our brain will perceive the difference in loudness between whispering and having a normal conversation as greater than the difference in loudness between hearing an orchestra and sitting in the front row of a rock concert. Hence, it is useful to have a scale that measures sound like the human brain does. This is the decibel scale, abbreviated dB. See if you can figure out how to convert from relative intensity of sound to decibels. Did you figure it out? To convert from relative intensity to the decibel scale, take the exponent of the 10 and multiply it by the number 10. 10 to the 16 becomes 16 times 10, or 160. 10 to the 14th becomes 14 times 10, or 140. And 10 to the 8th becomes 8 times 10, or 80. To write this in a more precise way, we might remember that the log of a power of 10 gives us the number of zeros that power of 10 has. For example, the log of 10 million is equal to 7 because it has 7 zeros, and the log of 10 to the 8th equals 8 because it has 8 zeros. So, to get from relative intensity to decibels, we take 10 times the log of relative intensity. Of course, we may also want to get from decibels to relative intensity. To do that, take 10 to the decibels divided by 10. For example, if we wanted to convert 160 decibels to relative intensity, we would find 10 to the 160 divided by 10, or 10 to the 16th. The table below summarizes the conversions. Notice, when converting from decibels to relative intensity, it is important to divide by 10 before making that quantity your exponent of 10. If you do this out of order, that is, take 10 to the decibels first and then divide by 10, you will get the incorrect answer. To avoid this possible order of operations mistake, you can use the following approximation for relative intensity instead. That is, relative intensity is approximately 1.26 to the decibels. Let's try this in the example below. According to the preceding table, the sound from a vacuum cleaner is about 80 decibels. An idling bulldozer produces a sound that is about 85 decibels. How does the relative intensity of the idling bulldozer compare with that of the vacuum cleaner? Let's use comparing division to solve this problem. I put the greater relative intensity in the numerator and the smaller relative intensity in the denominator. Since we are given the sounds in decibels but asked to compare relative intensities, we need to use our formula above to convert from decibels to relative intensity. We have the choice between using this exact formula and using the simpler approximation. Let's go ahead and use the simpler approximation because I think it's good enough for our purposes. According to our formula, 85 decibels has a relative intensity of approximately 1.26 to the 85. And 80 decibels has a relative intensity of approximately 1.26 to the 80. Since the bases are the same, we can go ahead and subtract the exponents. That is, the ratio of relative intensity is 1.26 to the quantity 85 minus 80, or 1.26 to the fifth power. This is not something I could do in my head, so I'll put this into my calculator. 1.26 to the fifth power is approximately 3.2. This means the sound from the bulldozer is about 3.2 times as intense as that of the vacuum cleaner. Example 6. Suppose we have a stereo speaker playing music at 60 decibels. What decibel reading would be expected if we add a second speaker? Note that adding a second speaker would have an impact of doubling the relative intensity. Would that mean the number of decibels would double? To figure this out, let's convert our decibels to relative intensity, then double the relative intensity and convert back to decibels. Ready? We begin with the fact that one stereo plays music at 60 decibels. To convert this to relative intensity, we'll use one of the formulas from above. Note for our purposes, this approximation will do the job. So according to the formula above, the relative intensity of our one stereo speaker is 1.26 to the 60 power. To double the relative intensity, we'll multiply this number by 2. We get that the relative intensity made by playing two identical stereo speakers at a level of 60 decibels each is 2 times 1.26 to the 60 power. If we wanted, we could plug this number into our calculator. However, we're not really concerned with what this number is. Instead, we want to know the decibel reading we should expect when playing music from 2 stereo speakers instead of 1. To convert from relative intensity back to decibels, we use the formula in the above conversion table. Decibels equals 10 times the log of relative intensity. So we need to take the log of our relative intensity and multiply it by 10. Now I will put all of this into my calculator. You need to make sure your parentheses are in the correct place. Otherwise, you risk taking 10 times the log of 2 and then multiplying that quantity by 1.26 to the 60. Instead, input into your calculator 10 log parentheses 2 times 1.26 to the 60th power end parentheses. The result is approximately 63 decibels. This result may seem counterintuitive. Adding a second 60 decibel speaker does not double the decibel level, which is the perceived loudness. Far from doubling the loudness, adding another speaker only increases the decibel reading from 60 to 63. This interesting phenomenon is roughly true of all 5 human senses, including sight, and is known as Fechner's law. The law states that psychological sensation is a logarithmic function of physical stimulus.